Okay, so we can start. So it's a great pleasure to have Professor Wolfram Barfuss with us. Kindly agreed to give a talk, which is very much related to what we are covering in this workshop. So just to quickly mention that he's a tenure-track professor of integrated systems modeling for sustainability transitions at the University of Bonn, Germany. And so his website says he's motivated by the question, are we smart enough for the good life? Um Basically dealing with models of collective learning. So he has a physics background, I suppose, but with a wide varied interest in all sorts of things. Um, so you see that the topic is very much related to what we were dealing with in the past few days regarding games, networks, and learning, and so on. So we are happy to have you here, Professor. Over to you.
Thank you very much. It's a real pleasure to give this talk relatively shortly before my winter break. So that's a great, you know, um, dart into that. I'll be talking about collective cooperative intelligence, and by the end of the talk, I hope you have a rough idea of what I mean by that. So you mentioned the question that sort of motivates me, and I found out that this is actually the question that motivates me for longer than I'm aware of it. Are we smart enough for the good life? And so what do I mean by that? First of all, what's the challenge? And in my view, the challenge of the 21st century is to achieve a good life for all within a healthy planet. So here you see a picture of the planetary boundaries and state of affairs as such that many of those are transgressed, highlighting that when we talk about sustainability and the good life for all in the long-term future, it's not about it's not only about climate change and the ecological dimensions, it's more than that, like biosphere integrity and others. So on the one hand, we want to stay below this safe ceiling, this ecological ceiling, um, and do not transgress these boundaries, these critical Earth system thresholds. But on the other hand, we don't want to have no impact on the Earth system because we want basic human needs fulfilled and achieve a social foundation for all. And here you see the famous Oxfam donut proposed by Kate Raworth for the first time in 2012. And just conceptually, inside this safe and just space, we want to achieve all the sustainable development goals and potentially future goals in the development agenda, and do that on a pathway safely away from catastrophic tipping elements in the Earth system, because we do not want to risk severe, drastic changes with potential catastrophic effects. So the crucial question is, of course, how how do we enter that safe and just space? And I think it is clear that we need urgent and large scale collective action. So, how do we as scientists contribute to this solution? Well, on the one hand, we raise awareness that there is a problem. And we've done so quite well, I think. There is not too much disagreement on the question whether or not we have a problem. So we know there is a problem. With more and more reports from the 1970s or so onward, we become increasingly sure. So we reduce the uncertainty that continuing as we've done comes with severe threats. On the other hand, we also know potential solutions. We know what to do, either technological or institutional. So there's lots of possible solutions. So it's also not the case that we do not know what we could do. And so that makes it sort of, in a nutshell, from 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 a few meters back, a problem of intelligence, which is roughly defined as the ability to solve all kinds of various problems. If we know what to do, we know there's a problem, we have the information, we have the actions. Why are we not acting? And So this brings me to the outline of my talk. I will first start with why there are cooperation challenges in human-machine ecologies coupled to human environment interaction situations. Then I will look at how we can move forward with these challenges, and the nutshell is by building bridges between scientific disciplines. And last, we'll be looking at what we find already now there, and then of course this is a research agenda for the coming years, but already now we see emergent phenomena in different contexts, in different cognitive aspects. So let's start with why cooperation challenges human-machine ecologies. So in a nutshell, it depends on us all. So it's not just that we can individually decide whether or not we want a sustainable future. It depends on the actions of other actors, whether that might be individuals, households, or actual real nation states. And so this framework, relatively recent framework about the planetary commons, ties this aspect, these nature's regulating and maintenance services that require cooperation, to the critical processes of the Earth system. So it integrates those two spheres quite nicely in a conceptual manner, in my view. So what's the challenge of collective action and cooperation? Well, very simply, that individuals have to pay a cost for the benefit of all, for the benefit of the collective. And so let's now play a hypothetical game between you and me. So we both can either choose to cooperate or defect. And so imagine that I would be cooperating, and you can choose between cooperation and defection. Then, according to the relevant the range of payoffs here between B and C, you would be better off defecting. B is greater than 2B minus C. So now let's assume what would happen if I defect. Well, then, because C is greater than 0, you also would be better off defecting. So regardless of what I'm doing, you would be better off defecting. Or the same is true for me. The situation is completely symmetrical, identical. And so the greed to exploit others and the fear of being exploited by others drive individuals to the faction. The individual interest goes to the faction. Now, the dilemma of it is that everyone would be better off if we would all cooperate. 2B minus C is greater than 0. So the collective interest points towards cooperation. And this is sort of a very simple game theoretic model. Maybe you've heard about the prisoner's dilemma, but it's conceptually, it ties very much to Gerd Harden's idea of the tragedy of the commons. So common solution approaches to this tragedy is that we need outside central authorities that regulate that situation through taxes or bans or other kinds of regulations. Or we need to privatize and do not have these common resources. And then individuals will manage their part optimally. So the idea. The problem is that this solution cannot work on the global level, on the planetary commons, because we don't have central outside authorities that could regulate that, where we have anarchy on the international sphere. But even another problem is that this is only a very, very, drastic picture. And this is not at all capturing the situation of commons, because pioneered by Eleanor Ostrom, the governance of local commons is very well possible without outside interests, outside central authorities. So I very much like this title of her book, The Drama of the Commons, highlighting that things are not as simple. The tragedy is not inevitable, and it is more complex than in the prototypical model. Human motivation is complex, and the resource systems themselves have dynamics that influence their response to human use. In addition, even if we have central authority, it does not guarantee us that they use the commons optimally or well. They tend to overuse them as well. And so she pioneered a different kind of solution approaches, including bottom-up approaches, decentralized governance, and social reciprocity. The problem, however, is that they also don't not seem to be able to scale to the global level. We have many anonymous relationships, so I'm monitoring problems or individual. We are very many actors, so there is something that makes these approaches not able to work. And a third element to the question of cooperation is also artificial intelligence and technology. Yeah, we are advancing this quite rapidly, but we need to be cautious that, well, whatever we do, maybe this also should be able to cooperate with us and with each other. So to help humanity solve the fundamental problem of cooperation, scientists need to reconceive artificial intelligence as deeply social. And this is roughly coined under the term cooperative AI. So to summarize the cooperation challenges, despite the tremendous research that went into this problem of cooperation, that in our view still exists in human machine ecologies, asking basically the question, why are we not cooperating more towards a sustainable future for all, is to consider the interaction of individual decisions in their environmental context, the collective behavior that emerges from that and under different social configuration. And crucially is that we need to account the dynamics of those interaction in a transparent way, because we want to understand what is going on. And this basically summarizes many perspective papers in this regard on human environment, social ecological systems modeling. So to summarize the first part, we basically ask the question, why are we not cooperating more towards a sustainable future despite knowing that there's a problem and knowing many solution approaches? And so to move on with that is, we need a transparent analysis of the nonlinear dynamics of the collective behavior emerging from individual adaptive intelligence in environmental contexts. How do we do that? In a nutshell, we're proposing to build bridges between scientific disciplines or communities, and those are, for better or worse in our assessment, complex system science on the one hand, and multi-agent reinforcement learning on the other hand. So, of course, you could argue, well, to what extent are those, homogeneous disciplines? And there might be other names. So, complex system science has a lot of evolutionary game theory influence here from this perspective. But nevertheless, let's take these two words as a focal point for our comparison. So in a nutshell, complex system science is very insightful, has been very insightful to the question of cooperation. It produced a rich understanding on how cooperation can emerge. The problem is that it tends to be a little bit simplistic. It ignores largely individual level complexity and also environmental context. Multi-agent reinforcement learning, on the other hand, is very rich. Yeah? It combines collectives of individually intelligent agents through reinforcement learning in changing environments easily. The problem is that it tends to be a little bit obscure in the classic traditional way and also modern way it is typically done. And so it's highly stochastic, computationally expansive, and therefore also sometimes challenging to interpret. And so we, just by looking at that, said, well, they have huge potential for complementing each other. The question is how. And so before I'm going to the specifics of how, I'll just briefly go through each of them individually, assuming that you have already quite some insights maybe especially on complex system science, given the title of the workshop. But nevertheless, just that we are on the same page of what I mean by complex system science and multi-agent reinforcement learning. So the key properties of a complex system is that we have a macro level and a micro level. On the micro level, we have often heterogeneous adaptive agents or entities that interact often relationally, so on a network, also a key theme of the workshop, in a shared environment with some nonlinear ways. And these interactions produce an emergent macro level, emergent collective behavior, which then typically feeds back onto the micro level. And the whole thing evolves in non-equilibrium transient dynamics. So this idea of equilibrium is not so important for a complex system. And the key phrase of complex system science is that the whole is more than the sum of its parts. And a beautiful quote that captures that by Peter Dodds is, "There is no love in a carbon atom, there is no hurricane in a water molecule, and no financial collapse in a dollar bill." So this is the complex system science is the study how macro level properties come to exist that don't exist on the micro level. And for the question of cooperation, I just want to highlight this famous paper by Martin Nowak on the 5 rules for the evolution of cooperation that also shows the kind of research that often is done under complex system science. So it states clearly 5 different mechanisms and relatively simple equations, conditions where the one mechanism becomes an equilibrium or cooperation becomes an equilibrium or not, or cooperation a possibility to be more precise. So this also highlights the kind of understanding this type of research is able to produce or produces. The challenge is that, well, it tends to ignore a little bit the individual level complexity or the environmental context. So sort of a key fundamental research challenge here on its own right, is what kind of complex phenomena emerge when the individuals are complex themselves or when they are embedded in some kind of complex environment. And this is far greater than the question of cooperation. But here we recognize this is also very important here for the question of cooperation. Now, on the other hand, multi-agent reinforcement learning starts with a so-called multi-agent environment interface, and there might be different names. There are different names for that, but all of them share that you have more than one agent. They can choose an action each, and those actions exert on the environment. The environment may or may not change its state, and as a result, the agents receive a reward signal for that transition and also observe the new state of the environment or some observation of that. Now, multi-agent reinforcement learning simply repeats that process, and you can think of a process of interacting with the environment during which the agents individually each assess their reward prediction temporal difference error, depending on which field you're in. You call it one way or the other. But this signal tells the agents how they should adapt. The second process of adaptation, changing their rule of behavior, their policy or strategy. And the goal is to get more reward over time. And you might value time differently, discount the future in some ways, but in general, you want more reward over time in the long term. The beauty is this is also mathematically well formalized, which is not the focus of this talk, but for those of you who might have heard about the Bellman equation, state values, state action values, they are all foundational to multi-agent reinforcement learning. So how does this play out in practice, cooperation in multi-agent reinforcement learning? First of all, recognizes that well, maybe cooperation is not immediately available. Maybe it's actually a strategy, a policy that I have to learn, and not just what I can do. And this is summarized by the phrase sequential social dilemma. And typical solution approaches are other regarding preferences, that you have influence on others, norms and reputation or contracts. So some of them are kind of mirrors of the complex system, evolutionary biology, evolutionary game theory side. Others are come from other influences. And here on the right, you see typical examples of these challenges, often in so-called grid world environments where you have some resources and a task like cleaning a river. And there's always this tension between individual interest and collective well-being present in some way or another. Just as a side comment, I think a key frontier here in this line of work is how to integrate large language models into these sort of situations, making it even more complex than maybe here in this sort of deep reinforcement learning phase where agents have a neural network to go from their perception to action. And now if they can communicate, it's even a higher level of complexity in the model itself. So, and those will only amplify the challenges that this can become a little bit obscure, highly stochastic, sample inefficient, computationally hard to run. Also a challenge for engineering in terms of implementation and tuning these models, hard to explain as a result. And sometimes the question, what is actually the minimal model? What do I want to model? So we need here, from that perspective, a transparent and lightweight analysis. How to do that? And now I think this is one of the more important slides of my argument, how to build the bridges. It's actually not a complicated slide, just 4 bullet points. First, we need to realize that our focus, what we are interested in, is building models for understanding. We are not so much interested in scaling up solutions, which a lot of machine learning work is driven by. Then we need to realize all models are wrong. You may have heard the famous phrase, all models are wrong, but some of them are useful. But even just all models are wrong gives us liberation, or the need really to ask about what is the most minimal model that we can work with. So also, from this idea, we should make things as simple as possible, but not simpler. So this, as a consequence, means let's study low dimensional environments, making the situation where agents are interacting as simple as possible, but not too simple. Right? That's the key phrase. So we will be using the framework of the multi-agent environment interface, but instead of looking at grid worlds, we make it much more manageable, much more simple in order to understand something. And the second aspect is controlling, doing some mathematical operations to mitigate the stochasticity of the learning process. And this is sort of summarized by what we decided to call collective reinforcement learning dynamics, emphasizing the dynamic aspect. And the idea is we treat reinforcement learning as a nonlinear dynamical system and develop what you might be calling deterministic limit approximations through averaging the strategies and the stochastic transitions of the environment, such that the temporal difference error, you can imagine becoming a deterministic temporal difference error given a current policy of all agents plus some noise. And then under some limiting process, we can eliminate that noise and arrive at a deterministic update equation of all agents' policies, being the old policies, times the exponent of the learning rate times this deterministic temporal difference error, delta x, and properly normalized. And conceptually, the idea is that agents learn how to act as if they have already a perfect model of how the world works, given all other agents for that current time step. So they do not anticipate how they would change, but for now, they take whatever they do into consideration to adapt their strategy a tiny or a step into the direction in strategy space that gives them a more reward over time. And sort of this approach that makes the ballpark of our work is building up on an interdisciplinary but scattered foundation from machine learning, control and engineering, statistical mechanics, economics, sociology, and mathematical biology. There it's important to recognize that there are different goals behind those lines of work regarding the biological plausibility of these learning dynamics and also the role of equilibrium. Sometimes it's crucial, sometimes it's less important. So to make it clear, our focus is to investigate the nonlinear dynamics. So we are interested more in the dynamics and, for example, the equilibrium of biologically inspired learning applied to the question of cooperation. So to summarize that part, we build bridges by bringing the level of understanding from complex system science to the richness of the framework where multi-agent reinforcement learning works in, and operationalize that by developing and studying collective reinforcement learning dynamics, which mitigates the noise in comparable low-dimensional environments, decision problems. So what are we able to find there? And I just want to briefly highlight how the Marl framework enriches the complex system science by basically giving us a framework to model cognition in different contexts. And this touches upon the challenges of individual decisions, environmental contexts, and collective behavior. So regarding individual cognition, I would view reinforcement learning really as a general prototype model for intelligent and adaptive decision making. So here you see two kinds of diagrams or conceptualizations, often tied to a reinforcement learning agent in sort of perspective pieces in the machine learning world. So you have action, observation, or it's called perception. You have a reward signal and some internal transition model or word model, and then some evaluation module. So I'm not saying that we know all the details here and we just need to translate it into a workable mathematical model. The details here are interesting research question on their own. The key point is that we can communicate with these with the science that looks at the details. We are compatible in that sense by taking up a reinforcement learning framework. So that is kind of the theoretical conceptual side, but also on the empirical side, it was found that temporal difference learning is actually well grounded in also biological learning, showing here the dopamine activation under different reward conditions. And it shows basically the same qualitative signature that also was found independently as a machine learning update. So the question of learning and how to learn in this setting seems to be solved both from engineering and evolution biology in a similar way. So this also gives me some indication and justification. Okay, however the details might be looking, the general frame is hopefully not entirely wrong. Embedded cognition, so what can the environment do? The technical term that we are working with is called the partially observable stochastic games. This involves quite a bit and is a bit technical, but practically it's a general model to model decision problems where the consequences might be delayed, can be delayed, so very far in the future, and stochastic, so it's not certain that a particular action leads to a particular outcome. And so by that, we can actually model kind of abrupt transitions in the environment, sort of think of environmental tipping points, but also more smooth dynamics, partial observability, meaning that agents are not 100% sure in which state of the environment they are in. You can also model spatial extended environments like these squid worlds, or even a social environment where agents basically react to what other, or in this case, the two all agents did in the previous round. So it's good to think of the environment being composed of a social environment and a natural or ecological environment. And this also means that just pure strategic interactions or noisy reward models feedback are included in this more general. And just a side comment, I really like to work with discrete mathematical models, discrete states, discrete actions, discrete time. I think has some conceptual power, this or beyond the obvious numerical compatibility. Ultimately, when we want to work with computer models, discretization is a useful foundation. And regarding the collective cognition, this is very, very straightforward. We are very general in sort of modeling anonymous interactions, networked interactions, and there could be different kinds of networks actually emerging. Agents can be heterogeneous, so that we don't have to assume that everyone is the same. And also some kind of hierarchical interactions could be modeled without too much complication. The challenge is rather than that we easily run into a curse of dimensionality with this framework. And here, ongoing research focus is on mean field approaches to mitigate these challenges. All right, so now in the last part, let's look at how complex system science is able to improve insights into the multi-agent reinforcement learning framework, applying this idea of collective reinforcement learning dynamics and uncovering some complex emergent phenomena. And sort of this cuts through our cooperation challenges by focusing on the emergent collective behavior, focusing on dynamics with a focus on transparent analysis. And we apply this to a sort of minimal model, sort of the most minimal model that you might be able to think of, where we have collective action from individual adaptive intelligent decision making through reinforcement learning in an environmental context. And the idea is that the two agents, they play sort of that prisoners public goods type dilemma that we played in the beginning of the talk, except that imagine the situation is now embedded in a environmental state that is still prosperous, that is still well. So agents can actually get a good reward, a good amount of well-being from that state. And now defection is not only socially suboptimal, it also comes with the risk of collapsing the environment. So each agent defecting increases the risk that the environment collapses. And if it collapses into the degraded state, agents suffer with a negative impact of collapse, and only eventually, after some time, probabilistically, recover back into the prosperous state. So this sort of models roughly this idea of an ecological tipping element. And what we find is, in summary, sort of the very standard phenomena of nonlinear dynamics, also in the learning dynamics, in the social learning dynamics on its own. From multi-stability critical or abrupt transitions, hysteresis behavior in different dynamic regimes. And in the remainder, I just go briefly through each of these phenomena, and then I'll wrap up. So here you see kind of a typical strategy space of these learning dynamics. Here on the x-axis, the probability for agent 1 to cooperate, given that we are in the prosperous state. And on the y-axis, the probability to cooperate, given that we are in the prosperous state, but for agent 2. And what you see here is that it depends on where the agents start, whether they learn to defect or they learn to cooperate. So there's a critical separatrix that separates the basin of attraction of defection to the basin of attraction of cooperation. So basic multi-stability. What does this mean conceptually? Well, on the one hand, this ties to a proposed measure of collective intelligence in self that was proposed by Naomi Leonard and Simon Levin, 2022. That basically says we should think of collective intelligence as the basin of attraction to the cooperative equilibrium. And this actually gives us a measure for collective intelligence. On another note, it is also related to the idea that here the collective itself can encode, in this case, with two equilibria, one bit, one answer to a yes or no question. So it's emergent collective memory that we are observing. It is also a geometric view on the question of how does ad hoc teamwork work? How can that work? And the idea is, imagine that we learned to cooperate and then you get a new partner. So a new partner will start with a strategy that is between 1 and 0. And so this geometric view allows you to see, well, here it doesn't matter, even if they do not, or I mean, maybe we cannot be entirely sure, but it seems like, so we would have to investigate it in more detail, but it seems like for a large part of whatever they do, like which probability they have to cooperate initially, they also would learn to cooperate in the long term. So we can assess the potential or the probability can ad hoc teamwork work also with this geometric view. And last, very important in sustainability and resilience science, the basin of attraction as a measure of resilience, like when unanticipated shocks might get the agents out of that equilibrium. What is their potential to relearn the cooperative or the defective equilibrium? So now let's zoom into this bundle of learning strategies here along this purple separatrix, and look at the trajectory over time. And there we see sort of an emergent separation of timescales. So it seems that agents learning is almost converged until a sudden and drastic fast changes happen again. It's sort of a social tipping, transient tipping phenomenon. So this is, of course, not too surprising if you know the underlying geometry. But suppose you didn't know that. Suppose you just perform a simulation, and then it seems like, well, maybe we are converged here, and they learn this mixed equilibrium. So this just emphasizes, if it's somehow possible to get this underlying geometry of the learning, you have a richer and better understanding for also these metastable states. Now, let's assume that agent 1 will have, starts with all possible, or like many possible initial cooperation probabilities on that line. So that orange line should be on that line where these points are. And then here you see how long does it take the two agents to converge. And what you see is that at the critical point, where they cross the separatrix, is sort of a critical slowing down of the inherent learning dynamics. So it takes the agents much longer, about an order of magnitude longer at this critical point as when they are far away. And so this suggests that, especially at those critical points, convergence is less relevant. And we need to focus more on the transient learning dynamics, but there's also potential to apply insights on early warning indicators from complex system science to multi-agent learning. Basically, the same insights translate also to critical or abrupt transitions in here the example of commons with thresholds. The key difference is that now we are not within the dynamics changing the initial conditions. Here we're changing a sort of parameter external to the dynamics. And the example we have here is the so-called discount factor, indicating how much the agents care for future reward. So what you see here, if they do not care so much about future rewards, they do not learn to cooperate, they defect. And if they care a lot for future reward, they learn to cooperate. But in between, there is this, phase where, they sometimes learn, they sometimes don't. And here on that transition phase, it also takes the convergence much longer to happen than, when they are in one of the other clear regimes. So in these plots, we basically study each situation for different discount factors individually. So there is no a time component between becoming more patient or becoming less patient. It's taken individually. If we do change these discount factors or any other parameters within the simulation, we can also observe the phenomenon of hysteresis, which imposes another form of collective memory and can be important for sustainability interventions and social tipping events. So what's happening here? Let's assume we start. So in the large blue point, we start a simulation with a discount factor here. This value of 0.6 is not particularly important. That is a value of 0.6. And in this case, you also see, okay, 0.6, they should learn to defect. Well, they learn to defect. Then we increase the discount factor. We increase until here, until this critical value. So this is sort of a first social tipping point where the agents learn to cooperate. And we can increase the discount factor further, and then we decrease it again. So imagine we have a campaign, agents become more patient, more future looking. They cooperate, success. Then we stop the campaign and agents become less future looking, or there's a crisis there and they have to focus on the now, and they become less future oriented. So the discount factor decreases again. But interestingly, the two agents stay at the cooperative equilibrium. So this is the hysteresis. It depends on where the agent's coming from. But of course, it has limits. There's another tipping point, and when that is crossed, they learn to cooperate. They learn to defect again, and cooperation becomes unstable. And the last element that we couldn't really find in this ecological public good, so I'm turning to a well-known, well-studied game, the sort of iterated prisoner's dilemma. And so when the agents cannot remember the past moves, or they just play an independent, unconditional strategy, either cooperate or defect, they just learn to defect. That's the Nash equilibrium. That's kind of very much in line with the equilibrium game theoretical prediction. When now agents condition their previous round's action, or their action on the previous round's action, so they are sort of have this social environment and learn cooperate or defect, given that in the last round both cooperated, one or the other defected, or both defected, then first of all, we see that they can learn to cooperate, which is in line with equilibrium game theory. It changes the game to embed these agents into this history one strategy space. But from a dynamic point of view, it's interesting that they also, have these much more interesting dynamics, some oscillations, and some kind of unpredictability here present. So to conclude, I ask, why are we not cooperating towards a sustainable future? And pointed out cooperation challenges in human machine ecologies we need a transparent analysis of the nonlinear dynamics arising from the collective behavior emerging from individual intelligence in an environmental context. How do we do that? By building bridges between complex system science and multi-agent reinforcement learning, bringing the level of understanding from complex system science to the richness of the multi-agent reinforcement learning framework, operationalized by the idea of collective reinforcement learning dynamics, which mitigates the noise in comparable low-dimensional decision environments. And by that, we're already able to find interesting emergent phenomena from various situations of cognition and contexts. So this is the corresponding article, a perspective piece, which is currently in press for a special feature in PNAS. And I'm happy to let you know when it comes out. If you are now interested to get your hands dirty, we have a really, really work in progress Python package where you can, start with this idea on the collective reinforcement learning dynamics, and any feedback on that is much appreciated. So we are working heavily on that. So it's not, I wouldn't say it's finished or polished in any way, but I hope it's usable in some way. And so to come back now to the initial question, are we smart enough for the good life? I think we don't know yet, but at least we have some clarity about what we need to focus on in posing that question. So instead of looking at intelligence as the mere ability to solve various problems, I think what is needed is a perception or an account of collective cooperative intelligence. And with that, I thank you very much for your attention.